I heard what Sheldon's supposed to be.
Oh, he's the Doppler effect. Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now.
There you go, Doppler effect. That's what we're talking about. No, we're not quite talking about that. We're talking about frames of reference. You know, when a car goes past you, it goes, the frequency changes because the radiation is coming towards you and then it's going away from you, so the apparent frequency changes. And so you know that from your physics. And so we will talk today, or begin to talk today, about conservation equations, part of which says this. So part of which is talking about frames of reference. And so it matters what our frame of reference is. We've already done some things related to that. Perhaps we don't need the music. And we need to be able to define exactly what the frame of reference is that we have. We talked about Bernoulli equation. We talked about how the fact that if you had a plane flying past you, the streamlines across the wing would be physically going past you. But if you attached yourself in the cabin to look out on the wing and were traveling with the plane, the streamlines would be in a steady state. It would always look in the form that it looks at when you started off, and when you get to Australia, it would look exactly the same. And so that is one of our requirements for using Bernoulli, for example. And so we'll look at that in terms of what we'll talk about today. We'll talk today about, or this week, about conservation of mass. Mass rate in equals mass rate out, and if they're different from each other, you get an accumulation of mass in a bucket. That's the simplest way of looking at it. But of course, that bucket could be moving as you're spraying fluid into it, or spraying fluid out of it, in which case you have to know what the relative velocities are of the jet which is coming out of the front of the boat versus the boat going. Simply put, if the boat's going at 1 meter a second and the jet's coming out of the boat at 1 meter a second, then the droplets of water are going at 1 plus 1, the vector sum of those two, and we need to be able to use that in what we will do. So Fire Department of New York is one way to demonstrate that. What else have we got? And yeah, something perhaps closer to home for many of you who are working in the subsurface or will be working the subsurface. Drilling. Drilling is not only used for petroleum. Obviously, it's a big thing in Pennsylvania. For I'm going to shut the volume off. Shale gas is a big thing in western Pennsylvania. But environmental systems engineers, you drill for water, look for contaminated water. And mining engineers will drill blast holes and drill exploration holes. Energy engineers, perhaps less so for the use of that, those things. So typically when you drill a hole, you will log it in some way. When you drill a hole, the drilling process is typically destructive. For the fastest penetration, it usually just breaks up the material at the tip and then kicks it up back as rock chips in the drilling fluid. And so you don't really get a continuous record of the strata or the structure of the strata as you go down. So one way to image it is to use wireline logging. So you get sondes, maybe they're 2 meters, 6 feet tall. They get dropped along the hole on a wireline and then brought up the hole, hopefully, on the same wireline. Sometimes those things have little spinners in them, so-called spinner log, little propeller. When it goes down, it measures the relative velocity of the water coming up or going down the hole. And so you can put it down and retreat it, take those two values away, and you know what the velocity of fluid might be in the hole, because it might be going up the hole, out into the formation, and being lost, and you'd like to know that. And you use things like gamma logs to measure clay contents to identify shales from the natural gamma radiation. And you use velocity logs to put a little impulse of a little shock into the ground and measure the seismic velocity as it goes along the hole to the top measuring point on the sonde. And so these are things that are placed down the hole. And you can also measure temperature, continuous with depth, everything you could imagine you'd want to measure in a hole you can measure. And the reason for that is because if you don't have core from the hole, which you don't often in these very fast advanced holes, then you want some way of being able to say what's down there. And when you amalgamate all these logs, the natural gamma ray log radiation, a neutron density log which shoots hydrogen, which shoots neutrons into the formation and measures the bounce back from hydrogen, water, sonic logs, spinner logs, caliper logs to see whether the hole is widened out in certain areas. When you put all that information together, side by side, you can make some predictions of what the rock structure is. And so that relates also to what we'll talk about today, and that's frames of reference. Because, of course, the frame of reference is that you're going down and you're measuring stuff along the hole, and that's what we'll talk about today. So that's where we're going today. Tests. Any questions, comments? Fair test? I thought it was a fair test. Of course, winners, losers. Some people are very happy, some people are less happy. You know what they look like now. So I'm not sure. I sent out the stuff, at least some information for you. They're pretty similar to last year's. If you look at, I was surprised, if you look at actually, so actually if you want to feel good about yourself, I remember seeing this yesterday. Sometimes I look through old classes when I get ready for this year's class. So in 2021, the YouTube video, I think the averages, actually this is it here. You see it doesn't change very much from year to year. But if you look at the, oh, I don't want that. I think the averages were 28, 39, and 46. So whatever we had in the 60s and low 70s is great. And I don't know why it was that this particular year, and I don't know why I only have 2021, since I've been teaching this class, 6.1, for the other years intervening that. But anyway, so the bottom line is, I think if it went well for you, then you've got the system down. If it didn't work so well, then recalibrate your system. 10% extra, so 70 points are on tests, and 10% extra is 7 points. Each one of these tests, I guess, is worth 6.66. And so you can basically, if one didn't work out well, that's okay, because there's some leeway. The presentations and the homeworks, you should be getting 100% on those. Presentations are graded generously, I guess I'd say. If you blow it off, you'd get a 70, but if you take it seriously, then you'd be at the top end of that range, 100. I think it's not difficult to get that. You have your groups. I see some people already assembling their groups. A few points of extra credit for the tests or the classes we missed last week, etc. And so, yeah, I'm not sure. Anything else we're going to chat about? So I think if it didn't work out great, then just, I don't know, recalibrate and do what would work for you. I know it would work for me, and I've told you many times. I'd go through prior exams. You have the solutions, you have the exams, you have the solutions. If someone tells you that they're going to be verbatim, then you know what from your past experience, whether it was verbatim this past week. You know whether everything that we talked about on the equation sheets and the review was enough so you could get your stuff done. I see an equation sheet left here. That's about it. Yeah. Necessary evil, yes.
Out of curiosity, was 2021 one of the virtual years?
Yes.
That
So,
explains great.
yeah, the first of the, yeah, it was. It would have been the first of it, right? Because no, it wouldn't have been the second. 2020 would have been the first. Fall of 2020. COVID was March onwards, right? So, and we did switch from, I think no one liked the previous, it's a necessary evil for this class, any class, I think, right? But it used to be a single exam on a Wednesday night, 8 o'clock till nominally 10, but people stayed till midnight. 3 questions altogether, and less coaching as to what the next question was. And the problem with that was that if you hadn't calibrated, then you had 3 questions all at once. So at least here, if things don't go well on the Monday, you can actually do something for the Wednesday and Friday. No, I think it's better. Okay. Okay. All right. So let's get going. So this week you should please go through 5.1 through 3. I guess the homeworks were just due last night, right, because of the test. And yeah, I guess they're all delayed because of the test. So we cut you a break for that. All right. So we're talking about control volumes. Just to be consistent with what we've done in the past, talk about what we would have done last week. It didn't change much from what we'd already done in week 4. We talked about Bernoulli. We talked about the fact that Bernoulli was equal to F minus MA equals 0. So that's kind of what this is. The acceleration term is this v squared over 2g on both sides. We have not talked about losses. Our system is a perfect system, so it is irrotational, it's inviscid, it has no viscosity. It's irrotational means it's not vortices falling off the back of the wing, incompressible, and steady state. And so it has to be steady state in that when we talked about individual systems, we drew this system here. Maybe it's the only system I can draw, which is that the streamlines around this would look like something. And that the velocity here at time 1 is same as the velocity here at time 10 or 100 seconds or 2 years later. So the velocities don't change, snapshot doesn't change. And we can write these equations between an upstream point and a downstream point. It doesn't matter which way we write it so long as there are no losses. But it does matter, and you perhaps should always be used to writing it from upstream to downstream because that's the standard protocol if we do have energy losses in the system. So we know that when you blow down a pipe, the pipe would get warm because of the energy that's dissipated by the friction on the walls with the air that's going past it. That's what these losses are, which we'll talk about with pipe flow. And this is the energy that we'd put in the system. So far we've only talked about this and this, and that's all we need to talk about now. But it does equal Newton's second law, and it is equal to 0 if the losses are there. What else? The other thing that we'd have talked about last week, which is useful just to recap, is that we can also think of this as not just stream lines. And so we're interested in flow along these. We're interested in flow along the stream lines. We're interested in flow normal to those stream lines. We talked about that. We said that that would be 10% of our interest, not 90%. Most of the time we're interested in looking at the flow as we go downstream. And so the other thing that if we need to solve between upstream and downstream, and we're missing 2 parameters in this one equation, we can't solve it. So what we can do is we can solve it by using what we call continuity, which is kind of what we're talking about today, but we've already covered it. And that is if you look within a stream tube, that the velocity V1, which is occurring across here, and cross-sectional area A1, and V2 within this stream tube, and cross-sectional area A2, they have to be equal to each other. Actually, they have to equal to the density of the fluid that's going. Typically, because it's incompressible, the density upstream is the same as the density downstream. Even with air, we said that we shouldn't use it for compressible fluids, but it actually works quite well for compressible fluids. And so this is what we call our continuity equation. This means that the volumetric flow rate, actually, the area times V would be a volumetric flow rate, which is meters cubed per second. But multiplying that by the density, which is kilograms per meter cubed, would be kilograms per second, right? So meters cubed per second times kilograms per meters cubed gives us kilograms per second. And so that's a standard way in which we would do it. So if you're a petroleum engineer, environmental systems engineer, you're working with porous media, the flow equations for those porous media are differential equations. They're derived by getting a continuity equation. A little cube, a bucket in says volumetric mass rate of flow in equals mass rate of flow out. If they're not equal, then net accumulates. If more is going out than is going in, it's net depleted. And if you're in the Central Valley, that means the San Joaquin Valley is subsiding as you deplete the water resources, etc. And so this is a fundamental requirement. And it's what we'll talk about for this week in different frames of reference. What else do we want to talk about? Okay. The other thing that we would have talked about last week is free jets. And I hate to be an ass, but that's a free jet question on your second midterm. And so you need to know how to solve those. And the idea is that you can write Bernoulli's equation here, P over gamma plus Z plus V squared over 2G at this point here. And you can write P over gamma plus Z plus V squared over 2G here. This is at point 2, point 2, point 2, 1, 1, 1. And then you just look to see what you know. Open to the atmosphere, no pressure. Elevation, Z, positive upwards. So this would be Z1. And the so-called big tank assumption. If the tank is big and it's only been drawn out by a small amount, the velocity on the surface must approach zero. Right? Bigger the tank, only a small amount of water is going out, so the drawdown of that tank you can think of as very slow, even though we're thinking of it steady state. And so that means that this is zero, V1. Pressure coming out is equal to zero. Elevation here is just the difference between these two. And V2 is not zero. So you can write this out as V squared over 2G is equal to Z1 minus Z2. And it's a standard result, which is V is equal to 2G, call it H, right? Because Z has direction as well, right? This is a height. Standard result. So equation for a free jet. It will always come out of this tank equal to this magnitude. If you write it down here, and your height is then H2, then, H3, then V3 will be equal to 2G H3. And I guess if you think about this, and this relates to what we're talking about today, and that is, since we're talking about Bernoulli being sum of forces is equal to mass times acceleration, say in the z direction, we know that acceleration in the z direction is dvz. Let me write it differently, sorry, uppercase D. Let me write it as this. This is what is called the substantial derivative or material derivative. And we did this already. We did dv. This, by definition, is velocity in the z direction. And we talked about this acceleration. So this is the acceleration that's attached to me. If I was going across the room a bit faster and accelerating rather than being constant velocity, this would be the accelerometer that's attached to me, which would be saying what that is. The other one, the convective acceleration, is my velocity and change of velocity here, which would give me the velocity that's attached to me. So if you're looking at me and plotting my velocity as I go across the room, from that velocity at a point and its slope, its change in location, would give me directly uppercase dv dt. And so this is attached to the fluid that's moving, or if I threw the fluid across the room, and this is what inertia is acting against. But typically, if we know what the velocities are around an airfoil as we go downstream, this is the information that we have that we need to convert to this. And so that's all this is. And we said last time that this is equal to, another standard result is a half d v squared ds. Right? It's a standard result. We talked about how you get from one to another. And so if you write this v is equal to 2gs square root, oops, and say this s is the streamline. So a streamline that comes through these 3 points is this. We can think of this as s. And so if we take this and we do this to it, so if we calculate, substitute it in here, then this is equal to a half times the v squared is 2gs. Derivative of 2gs is 2g. So dv z dt is g. So a tank that's coming out, all it is just water falling under the action of gravity. That's all it is, nothing more than that. So fluid mechanics and solid mechanics is no different from your dynamics. All this is it's accelerating with gravity because it doesn't have any other forces acting on it. And so I guess the other interesting thing you'd be able to tell from this is that since, okay, so that's an important feature. So it's coming down, it's coming out with gravity. And so we can always get the streamline velocity from this equation, and it's just by using Bernoulli. It is always a streamline velocity. So if our tank looked, for instance, like this, then the velocity coming out of the tank, v2, would also just be given by whatever this height is. So in this case as well, if this is the height, h, then this velocity v2 would just be 2gh square root. Be going horizontally, because this is a streamline. So the streamline is what comes down here and goes out here. And so you can calculate that. And if this was directed in some way as well, you'll see these questions, then this is also the streamline velocity v2. So if you had a velocity coming out like this, I'm spending too much time on this, then this would have two components. It would have Vx and it would have Vz. And of course, if you knew the angle of this, you'll see this in the class notes that you'll look at this week. So it has a vertical component. So Vz is coming out of it at some velocity, 2gh. So it'll go up, but it will stop going up when it loses its momentum. So it'll go up and it'll exchange its kinetic energy, v squared over 2g, for potential energy as it gets higher. If actually this jet was directed directly upwards, it would go up the height of this water in the tank. If it's directed at an angle, then the velocity in the vertical direction will be less than v2 going upwards because it's at an angle, and so it'll take an arc, which won't be as high as the tank. And so all that you know is that, what is it, Newton's first law or third law? Every object moves along until it's acted on by something else. So this horizontal velocity won't change. So it'll always go horizontally at this velocity as it's inclined. But it will go up only for the amount of time it takes to reach its apex. And at that apex, it will have gone a certain distance. So you can always calculate what that distance would be by knowing how long it takes to get to the apex, and the distance it would travel horizontally would just be the velocity in x times the time to apex. Fine. There isn't one of those questions on the test, but you'll see those, and that just explains what's going on. So that's making the point that we need to use convective acceleration, and this is actually the substantial derivative is what we need to attach to Newton's second law to be able to define that. I guess the other thing is that also comes out of this, which I guess would probably, I think we'll talk about it this week. By definition, if we know that V3 and V2 are given by these terms, then we know that V3 is greater than V2, right? Because H3 is larger. It's not in the z direction, it's the distance below the free surface. So the other thing I guess we'd know is that this jet has to be thinning down because of this equation here. So if this velocity is increasing, then the cross-sectional area has to be decreasing because the volumetric flow rate or the mass flow rate across it has to be the same. And that just makes sense. And so this continuity relationship is what we'll talk about this week as well, but it was introduced last week. So along a stream tube, you can just define it. Okay? What else? Maybe too much math. So the reason, if we're dealing with Newton's law, we have this expression in each direction, right? So we said before that we have the sum of the forces, and what this means is that this is Fx equals mass times Ax, Fy equals mass times Ay, and Fz equals mass times Az. So that's what this expression means. There are three forces, x, y, and z, and there are three accelerations written as a matrix. Let's not worry about that now. Let's just talk about one of them. And what we would like to do is that we're going to write this as a substantial derivative, dvx dt. Looks very complicated, but it's not. And what we want to do is we just want to split it up in the same way that we did here. So what we can do is we can write out dvx dt. They should probably be partial derivatives, but don't worry about that. And I'm going to write out three components, dvx dt plus dvx dt plus dvx dt. And then I'm going to look at these components relative to the four directions, right? Time is kind of a 4D seismic is time and x, y, z. And so I'm going to multiply this by dx, dy, dy, dz, dz. And so coming out of that, then the change in x with time is just going to be velocity in the x direction. The change in y with time is just going to be the velocity in the y direction, and the change in the z coordinate that you're going through with time is just going to be the velocity in the z direction. And so this substantial derivative is just this. It's going to be the change that occurs with time, which we've said for Bernoulli doesn't happen, so this is 0. And this is going to be velocity in the x direction times dvx dx. This is called the convective acceleration in the x direction. The velocity in the y direction multiplied by dvx dy. And the velocity in the z direction times dvz. Sorry. I got that wrong first time, right? This vx dz. And so this means that if we know what these, it's a bit esoteric, we won't use it very much. So it means that if we know what the velocities are, as you plot my velocity with x as I go across this room, if you know the slope of that line and its magnitude of velocity, you have dv dx, which is the slope, and you have the velocity at that point. And so you can calculate exactly what my acceleration in the x direction is from this so-called convective acceleration. So this is convective acceleration, ACCN. Each one of these is convective acceleration in x. So, right? And so if we have time, we'll do a quick example. I'll come back in a second to make that point. But there's an example in the bottom. If we assume we know what the velocity field is in x, vx, vy, and vz, then we can just do the differentiations to get it. But we never have that information, so it's a bit esoteric. So let's do something that perhaps is more obvious. And that is using the reason for doing the borehole geophysics stuff in the first place was that let's think that we're using borehole geophysics to get the temperature profile with depth. And so we have a borehole, and we have z is positive upwards, negative downwards. This is temperature. If you know that you perhaps don't know, if you go down in the Earth's crust, the rate of change of temperature with elevation, anyone know? It's about 25 centigrade to 50 centigrade per kilometer. Plate boundaries, the Geysers geothermal field in California, it's on a plate boundary, 50 centigrade per kilometer, so you have a geothermal field. Underneath the crust here, where we sit, is probably closer to 25. And so this would be the slope of this line. If you go down a kilometer, then you would be at 25 centigrade. So you're going to send a sonde down here, and that sonde will record with time as it goes down. And so if you want to write the substantial derivative for the sonde, let's only worry about dt. That is equal to the rate of change of temperature with time plus the rate of change of temperature with depth, dt rather. We multiply by dz. And then if we go down here and we want to know what the temperature is at any particular time, then if we go down at a velocity of 1 kilometer per hour, not very SI, and we go down 1 kilometer, then this would give us the rate of change of temperature if it was attached to us. If we're sitting on the sonde as we're going down, This is 0. So if we look at this profile of temperature with time, it sits here now. If you look at it in 10 minutes, it hasn't moved. And so this term is by definition 0. The change in temperature with elevation is this, which is actually minus 25 degrees C per kilometer, right? This term here. And if we're going down, our velocity is going to be minus 1 kilometer per hour multiplied by. And so the rate of change of temperature as we're going down is equal to 25 degrees centigrade per hour. Just from the product of these. That's really all it is. And so if we wanted to be fancy and said also that the temperature changes with time, so say for some reason that the temperature changed and it changed from being 0 at the surface to being some amount. So if it changes here, and this is dt dt, I don't know. So this is 5 degrees centigrade per hour. Then all that means is that if we want to calculate the change in temperature that we see as we go down on this sonde, now it would be equal to dt dt plus dt dz times dz dt. And if I just write in those numbers, this is no longer going to be 0. This is going to be 5 degrees centigrade per hour. This is going to be just as it was before. This is 25 degrees C per kilometer. And this is 1 kilometer per hour. And so this is going to change the rate at which it will be. Instead of being 25 centigrade per hour, it will be 30, I guess, right? And it will be additive. These are negative. This is minus, and this is minus. And so this will be 5 plus 25. Same units, apples to apples. So that's really all the substantial derivative. It allows you to change a reference frame so that the uppercase dt is me as I go down, lower down the well, attached to this sonde, and it's what I feel. But if you look at this unchanging plot and look at these locations here, this is a constant. Well, this is just this, right? This is dt dz, nothing more than that. And it stays constant because it's a linear system in this particular case. Okay? So, bit of a long way to do that, but that's it. Okay? And so we need that because we will be using different reference frames. Okay? What else today? So that's it. So the other thing that we will think about, some math. Actually, we've done everything that we need to do. Is to think about different reference frames, and it gets. So we've talked about moving across, attaching something to a reference frame as you go across the front of the class, and so we can talk about reference frames which come in different flavors. They're fixed control volumes, moving control volumes, and moving and deforming control volumes. And so the best examples of these I can think of would be a fixed control volume. It could be a bucket. A bucket, you're pouring water in at 4 liters a minute, pouring it out at 3 liters a minute, you're accumulating at 1 liter per minute. That's all it is. Could be a portion of a pipe that or a stream tube. I guess this could be our stream tube, right? We think about this as a stream tube as you go across the top of your airfoil. It'd be a streamline on the top and it'd be a streamline on the bottom. Together that makes a stream tube. And this could be, for all intents and purposes, this could be our control volume in here. And of interest to us, I guess, would be that because a streamline is the direction that a particle goes, then we know that the flow across this boundary must be zero. There can be no flow across here. Likewise, the flow across this boundary has to be zero as well. And so the only velocities we're interested in would be the two velocities that are, I guess, influent and effluent. And so we could write V1 A1 equals V2 A2. And if we wanted to be rigorous, we could do it in density, because it could be that the gas going through here compresses and becomes more dense as it goes from upstream to downstream, even though we say that violates Bernoulli's law. And so this is just a fixed control volume that's static relative to the observer. If you look at a jet engine, then that could be fixed if it's sitting on the ground, but it's moving but not deforming if it's moving on a plane, right? It's the same shape, so the shape and size of it don't change as it translates as you take off. As air comes in through the upstream and goes out slightly faster through the downstream, it violates our conservation of mass because we're producing chemical energy, we're burning stuff inside that comes out, so don't worry about that for now. But this could be a constant volume segment which is translating, in which case it would be a moving volume. That's a fixed volume but moving. And the best example of a fixed and deforming control volume would be blowing up a balloon and just letting it go. So it goes in the air. So it's taking the mass that was originally in it and it's squirting it out. As it does that, the size of the balloon has to contract to be able to do that. And we can also write complicated equations that allow us to do that. And we probably will next time. So that's it. So that's where we're going. So important. So the message is this substantial derivative is important because it allows us to write things in viewing things that change in space, but linking it to a particle that's moving along that streamline, or the sun that's going downhill, down the hole. I don't know that we need to look at this. I guess maybe just talk about this final example. If for some reason we knew that at a point in our coordinate system, our wonderful coordinate system, whoops, didn't want that. So this is x, this is y and z. Yeah, x, y, z. And if we had a velocity which was changing in the x direction, it's a velocity which is, so this is Vx, what we've called Vx, what we've called Vy and Vz. I think this is what the book uses. So if we have something that's going at the velocity 2, minus y is not so easy to draw, but minus y would be off here somewhere, right? And see? So this would be 1 times z, right? This would be minus 1 times y, and this would be 2 times x. So these would be velocity. So I guess the net velocity for this vector would be this. That would be this vector. I guess we could call it v bar, under bar. And so if we knew what these velocities were, if we did, I don't know why we should, then we can calculate what the accelerations are in terms of these convective accelerations. This top equation here is the one that we just derived. Let me zip back to it quickly so I just remind you of it. This is the one we just derived here. We did it only for x, but we could do it equally well for y and z. And if we'd done that, then if we know what the velocities are in Vx, Vy, and Vz, then we can calculate what these components are. It's not changing with time, so these would all end up being 0, just because nothing's changing with time. Guess I should put it on here. These are finite, but there's no change. They're the same at second 1 as they are at second 10, so there's no change with time. And so this would be Vx times dVx dx. And so this term would be what? It's getting crowded, I know. So Vx is equal to 2x. And dV dx is equal to the derivative with respect to x of 2x, which is going to be 2. I won't put a times in there because it's confusing it. So it should be 4x, right? Yeah, it's exactly what it is here. And likewise, these terms, the off-diagonal terms, are all zeros because the change in Vx with y Vx only has a component in the x direction, so it doesn't change at all with y. So this has to be 0, and this has to be 0 as well. In fact, if you take Vy and differentiate with x, it's nothing, right? So it doesn't change with x. And the only other terms would be this term here is Vx times dVx dy. No, wrong, right? Sorry. This is y, right? I know it's getting confusing. Ux, Vx, Vy, Vz. And so this would be what? So Vy is minus y. It's very esoteric. And the change in Vy with y is minus 1. Derivative of minus y with y is 1, minus 1. So this should equal plus y, hopefully. And the last one would be Vz times dVz. It's all very esoteric, right? And what would those terms be? Velocity in the z direction, I won't do it, this is z, times the derivative of the velocity in the z direction, this is just plus 1. dz is just 1, right? And so this should be just z. So the numbers should be 4x, y, and z. Hopefully they are. 4x, y, and z. Just math. You never know what those vectors are, but that's what they mean. But really, the thing you have to get in your mind is that you're taking an acceleration that's attached to a particle of fluid, and Newton's law requires that the inertia forces that are attached to that packet of fluid depend on that uppercase dv dt, its acceleration. But you don't know what that is because you have a static reference frame and you just see that velocity changes with x. And so from the slope of that dv dx and its point Vx. You can use those two to get its convective acceleration. And of course, that's what occurs. Actually, that is what is embodied in this term. This is the convective acceleration. This is mass times acceleration. And so we do it by taking the velocity at a point, because we know that dv dt is also equal to a half d ds v squared. This is where that comes from. So that's exactly mass times acceleration. That's it. So that's all I wanted to chat about today. Next time we'll talk about filling buckets from the perspective of a fixed bucket that doesn't move, for a bucket that doesn't change in shape, size, but moves, and a bucket that changes in size and moves. And that's what we'll do next time. Okay. All right. Thanks very much. Thanks for your diligence last week.